Uh, Welcome, everybody. It's my great pleasure to introduce Håkan Andréasson. Sorry for the pronunciation. I'm sure I'm screwing that up. Who has been doing an enormous amount of work on Einstein-Vlasov, which is a subject that greatly interested me. And we're very happy to have him give a mini course today and on Thursday. And please, the floor is yours.
Okay, thank you. I should just admit one person here. So thank you for the introduction, and just a little bit difficult for me to see. Oh, maybe that is better. Okay. So thanks again, Martin, for the introduction. So you were worried about the pronunciation of my name, so it's actually Håkan, the A with a circle above. Anyway, so I would also like to thank you for inviting me to give this mini course. It's a pleasure. And I will talk about two topics for the Einstein-Vlasov system. This will be about gravitational collapse and properties of static and stationary solutions. So let me see if I can do this. No, it didn't work. Okay. Yes, okay. So the outline is that today, we call it lecture 1, and then I will talk just generally a little bit about kinetic theory and the Einstein-Vlasov system. And then I will focus on gravitational collapse, and there are many questions one can ask about gravitational collapse. And I will discuss conditions on initial data which guarantee formation of black holes. I will talk about gravitational collapse in the case of dust and Vlasov matter, because it is related but also quite different. I will discuss a little bit about critical collapse, and then I will, at the end, talk about weak cosmic censorship in the axisymmetric case. So weak cosmic censorship will be a general theme, of course, when I talk about gravitational collapse, but particular at the end, I will do something in the axisymmetric case. And in the second lecture on Thursday, I will focus on static and stationary solutions. So I will discuss massive and massless solutions surrounding a black hole. I will discuss axisymmetric solutions, and I will talk a little bit about stability issues concerning those static and stationary solutions. And just a general comment before I start is that the last 1 or 2 decades, the mathematicians who have been studying the Einstein equations, they have mainly been studying those equations without symmetry assumptions. And as we know, there have been big breakthroughs recently with the stability of the Schwarzschild and Kerr black hole and so on. And those results are, of course, extremely impressive. And what I will do, I will actually consider restrict myself to spherical symmetry or axial symmetry, which is quite different in the sense that the Einstein equations are much less complicated, at least in the spherical symmetric case. On the other hand, compared to those general results, they typically consider vacuum, or if they include matter, then the name of the game is to show that matter doesn't make a big difference. That is, the matter is normally initially very small. In what I will talk about is the opposite. I will mainly be concerned with situations where matter really plays an important role, and I will consider large data, basically. And in particular, even if we restrict ourselves to spherical symmetry, as we will see, the most central problems are actually open, also in this case. So I will discuss this. And just one question, because on my screen, there is sort of a bar covering the title, but you see the title, right, of my slides. Is that correct?
Yes.
Or, yeah, okay, good. Yep. Because it's some kind of bar from Zoom. Okay, so let me just say something general about kinetic theory, because in the Einstein-Vlasov system, then the right-hand side, which is the Vlasov equation, that is part of kinetic theory. And kinetic theory is a topic by its own right. It has, in principle, nothing to do with general relativity. And the fundamental, I have to admit, a lot of some people here. So if I am interrupting my speaking, that is because I have to admit some participants here. Okay, and the sort of fundamental quantity or object in kinetic theory is what I now call the microscopic density function F. So, because in kinetic theory, you consider an ensemble of particles, and depending on the physical situation, those particles can be atoms, molecules, ions, or in the situation we are mainly interested in, the particles are stars, galaxies, or even clusters of galaxies. But in kinetic theory, the common divisor, so to speak, is the way you model such an ensemble of particles. And you do this by this microscopic density function F, which is defined on phase space. So it depends on space, time, and momenta. And then to get macroscopic quantities, you simply integrate with respect to momenta. And there are different macroscopic quantities you can obtain. From this here, I only typed a very easy example in the sense that the kernel is 1. So more generally, you have a kernel which depends on the momenta here, and then you can generate, for instance, pressure, radial pressure, tangential pressure, and so on. And brief history of kinetic theory, I think the first one who came up with this kind of model was Bernoulli in 1738. And then there have been many names associated to it. So it's not fair here to just mention Maxwell and Boltzmann, but they are at least well-known people. And Maxwell is well-known for his equilibrium distribution when you consider a gas as the Maxwell distribution. And Boltzmann is, of course, well known for introducing the Boltzmann equation 1872. And examples of equations in kinetic theory are the Boltzmann equation, that is when you model a neutral gas, and the main interactions then are collisions between the atoms or molecules. And this is a quite complicated so-called collision operator that you take into account then. The other equations I have listed here, there are other generally more kinetic equations one can mention, but those are maybe the most standard ones. And the other ones on this slide, they are collisionless in the sense that you do not take into account the collision between particles. There are other fields that are the dominating fields for which determine the behavior of the particles. So for instance, in the Vlasov-Maxwell system, that is the electromagnetic field, which is generated by the particles. That is the main force. And this is used in plasma physics, in tokamaks and so on. And you can also consider the Vlasov-Panson system. And here you have two cases, the repulsive or the attractive case. So if you ignore magnetic fields, you can actually consider the Vlasov-Panson system also in electrostatics. But in particular, in what we are interested in here, it describes a system in Newtonian gravity, a collisionless system in Newtonian gravity. And then we have what we will mainly talk about, the Einstein-Vlasov system, and that is in the framework of general relativity. Before entering into general relativity, let me just mention a few milestones and open problems in what I call non-relativistic kinetic theory. So non-relativistic, I really mean not general relativistic theory, but still there can be special relativistic effects taken into account. And one of those milestones is for the Boltzmann equation, where Lyons and Diperna showed in 1989 that solutions exist globally in time, but those are extremely weak. They are called renormalized, and for instance, you don't know about uniqueness. But this is a celebrated result and was one reason why Leon's got the Fields Medal. And then a result which is very important for us is that in 1992, independently, Pfaffel-Moser and Leon's per term showed that solutions to the Vlasov-Poisson system exist globally in time for any data. And this is in both the attractive and the repulsive case. I will get back to that result later in those lectures. And then I should also say that people study stability of steady states, and a lot of work has been done on that during the years for the Vlasov-Poisson system, and in particular results by Yang and Gerhard Rhein. But the most general result was published in 2012 by Limon, Mehatz, and Raphael, where they obtained a very general stability theory for the Vlasov-Poisson system. I should say, and that I will say on Thursday, that in the corresponding theory for the Einstein-Vlasov system, it's very open, the nonlinear stability problem there. And then I should also say that for the Vlasov-Maxwell system, there is a very well-known open problem, and that is to try to show global existence in the 3-dimensional, 3+1 dimensional case. And it is known that if you reduce the spatial dimensions to 2, then Glasser and Strauss have shown global existence, but it is not known in the full 3+1 dimensional case. Many well-known mathematicians have tried to solve this problem, but so far without success. And let me just make one remark that this result on the Vlasov-Poisson system plays in particular an important role for us. And I should, when I was a postdoc in Princeton many years ago, and I interacted a little bit with Christodoulou, and he stressed the following fact, that if you should couple a matter model to the Einstein equations, it should first be understood in Newtonian gravity. And this is roughly what this result by Pfaffel-Moser and Leon's per term does, because having this result, we can say that we understand how kinetic matter behaves in Newtonian gravity. Okay, so let me say something about the Einstein-Vlasov system. I should move this bar because I cannot see my title. Can I do that? Oh, it's okay. Maybe I can move it like that. Okay. So the topic is the Einstein-Vlasov system, and the particles in this case, they are stars or galaxies or clusters of galaxies, and they interact through the gravitational field created collectively. And of course, you can use this model, the Einstein-Vlasov system, in cosmology, where you model the entire universe. But in this lecture, I will focus on the asymptotically flat case, and I will impose either spherical symmetry or axial symmetry. And this system, and we will mention some of those results later on, but just to make a summary, that to indicate that it has rich dynamics. So in particular, if you pose small initial data, then your solution will disperse and you have global existence. Whereas, as we will see, you can also specify large data which give rise to formation of black holes. And there is a rich class of static and stationary solutions, and they can be both stable and unstable. And you can also construct, as we will see on Thursday, stationary solutions with an ergo region. An ergo region is normally associated with the black hole, but those stationary solutions, they are regular and have no singularities, but still they are so relativistic that you have an ergo region. Another interesting thing is that if you take a stationary or static solution and you perturb it, the perturbed solution might oscillate, seemingly periodically, although it's not known. It's numerical results that indicate this, but this is open problem to really know what's going on. Okay, and so let me now try to formulate the Einstein-Vlasov system in the mathematical terms. And you have a space-time M and a metric G, and you put local coordinates on the tangent bundle, call them X and P of the space-time. You can also use the cotangent bundle, and that is what is actually more frequently done, but I have here used tangent bundle formulation. And an important quantity studying the Einstein-Vlasov system is the mass shell, which I have here given in the massive case. And then I should say that in my particle ensemble, I have assumed that each particle has the same mass, and I have normalized this mass to 1. So this means that this M here is simply taken to be 1. And then the mass shell consists of those 4 momenta, such that when you contract with the metric in this way, you get -1. And you pick the 4 momenta with component P0 to be greater than 0. So you get the future direction. And this mass shell is invariant under geodesic flow. And so the particles will follow the geodesic of space-time. And this P0, if you have this condition up in the mass shell here, you can, if in most situations at least, express P0 in terms of P1, P2, and P3. So this means that your coordinates on this mass shell can then be chosen to be T, X, A, and PA, where A now ranges from 1 to 2, 1, 2, 3. So this means that you have 7 coordinates on your mass shell. And this is reflected in the way the variables for your density function F, which now depends on those 7 variables. And this function F should satisfy what we call the Vlasov equation, which expresses again the fact that particles follow the geodesics of space-time and there are no collisions. If you have had collisions, this right-hand side, which is 0 here, should not be 0. It should be replaced by a collision operator. You see in the Vlasov equation, you see that the Christoffel symbols are included, so that this gives the coupling to the metric. And if you have a solution to the Vlasov equation, you can define the energy momentum tensor in this way. So you see that you integrate your F with respect to the momenta, and then you see that you have a kernel here depending on the momenta itself. Here you have lowered indices by the metric. So you get different kernels depending on which component on the energy momentum tensor you look for. And then when you have constructed this energy momentum tensor, you can simply write down the Einstein-Vlasov system. And here I've ignored the cosmological constant because I'm mainly interested in the asymptotically flat case. And this system has very nice mathematical properties, which has been shown during the last decades in terms of many global results. And one reason why it has nice mathematical properties is that all energy conditions are automatically satisfied. So the weak energy condition and the strong energy condition and the dominant energy condition are always satisfied for Vlasov matter. And if you, for instance, study fluids, this is certainly not always the case. Okay. So now I will focus on gravitational collapse. And one can ask many questions related to gravitational collapse. Probably the most important question is if weak cosmic censorship hold, and it is sufficient to specify to the spherical symmetric situation because that is still an open problem. And but there are other questions in gravitational collapse you can pose, and which some of them you can answer. And I have typed in blue here some of those which I will consider in more detail. I will say something about all those questions that I have on this list, but the ones in blue I will say a little bit more on. So one of those is, can conditions on initial data be specified which guarantee the formation of black holes? And this we'll see is the case. And then if so, can the initial data be far from possessing a trapped surface initially? And we will also see that one can do that. So you can be far from having a trap surface initially. And I've already indicated that if you take small data, then you get dispersion and therefore resonance. And this is the case for Vlasov matter. But another question one can ask actually, can solutions which form black holes exist globally in time? And then I mean in certain coordinates. And it turns out to be the case. So we will see that we can construct initial data which lead to formation of black holes where the solution actually exists globally in this case in Schwarzschild time. And then I will discuss the relation between Vlasov matter and dust in gravitational collapse. And why this is interesting is that, as we will see, in the case of dust, you can pose initial data that lead to naked singularities generically. So in that case, weak cosmic censorship is violated. And then the question is, if we take such data, because Vlasov matter can approximate dust arbitrarily well. So then you're curious what happens if you take such data for Vlasov, will you still get naked singularities or not? And one can of course ask more generally, this kind of data for dust, this particular set of data, can you find data of any kind which lead to formation of naked singularities? Then weak cosmic censorship may still hold because it is necessary that those data are generic. And then you can also ask questions about critical collapse. Critical collapse is a subtopic in gravitational collapse. And then typically you distinguish between type 1 and type 2 matter. And we will see that Vlasov is type 1 matter. And then finally, I will discuss something about the weak cosmic censorship in the axisymmetric case. And those results will be numeric. So before entering into some mathematics here, I just have a list about some publications where I have taken what I talk about today. And in particular, I want to do this because then I can mention my collaborators. So in particular, my collaborators are Gerhard Rhein and Markus Kunze, and also Ellery Ames and Oliver Rinne, for those results that I talk about today. And moreover, if you are interested in some of the details about what I'm talking about, you can find them roughly in those papers. Okay, so the list of problems I just I mentioned in a couple of slides ago, I had this gravitational collapse, and then I asked different questions. I will say something about each question in chronological order. And the first thing I want to comment just generally about is weak cosmic censorship. So in spherical symmetry, even if the equations are not that complicated, it is still only in two cases you really know a rigorous answer to the cosmic censorship conjecture. And that is for dust. And Christodoulou showed in 1984 that weak cosmic censorship is violated in this case if you take certain type of inhomogeneous initial data. The more the celebrated work by Oppenheimer Schneider from 1939 that we will discuss more later on, that is when you take homogeneous initial data. In that case, weak cosmic censorship holds. And then there is also this case of a scalar field, where Christodoulou has showed in a series of papers that there exist initial data which develop naked singularities, but that nevertheless weak and actually strong cosmic censorship holds. So in those two cases, they have thus different conclusions about weak cosmic censorship. But those two cases, they are more or less, scalar field is a toy model for matter, and dust is a rather naive model where you have no pressure and so on. So it would be very desirable to answer this conjecture in the case of Vlasov matter, which, but at the moment, this is actually an open issue. So let me now go to this question about black hole formation for Vlasov matter, because that's a question we can at least answer. And so the question is, if one can construct initial data which lead to collapse of a black hole, so that at least for such data, the weak cosmic censorship holds. And in order to investigate this issue, it is natural to choose coordinates which admit trapped surfaces. And I have studied this together with Gerhard Brine in Eddington-Finkelstein coordinates 10 or 12 years ago, where we proved the formation of trapped surfaces. However, in the present presentation, I have chosen to use Schwarzschild coordinates, which do not admit trapped surfaces, but I find them more intuitive. And we will see that also in those coordinates, you can show that a black hole forms. So let's do some mathematics then. So I will now specify to the spherical symmetric case and formulate the Einstein-Vlasov system in Schwarzschild coordinates. So the metric then is parameterized in the following way. You have two metric functions, mu, depending on time and area radius, and lambda. And you use and the r is the area radius. And you also have some boundary conditions to ensure asymptotic flatness. And then you can write down the Einstein equations, and which is not common. So standard in Einstein equations, it's that you can fit all the equations on one slide, but here it's certainly easy to do that. And on the right-hand side, now you have the rho, which is the energy density, P is the radial pressure, J is the current, and PT is the tangential pressure. In fact, those equations are not independent, and typically you only consider the first three, and if you also solve the Vlasov equation, the fourth one will actually follow. And before specifying how this energy density and pressure and so on is described in terms of our function f, let me just say that in this case where we have spherical symmetry, we typically use coordinates which are adapted to this symmetry. So therefore, here f will now depend on the coordinates time and the area radius, and the momenta variables in this case we denote by W and L, where W you can think of as the radial momentum, whereas the capital L is the square on the angular momentum. And one reason why this is useful is that the angular momentum is actually a conserved quantity, and this is reflected when you write down the Vlasov equation, because you do not have any derivatives with respect to L here. Only in the momentum variable, the only derivative you have is respect to the radial momentum. And I have introduced a notation here, which I call capital E, and that is basically for the particle energy. So the 1 here is due to this assumption about the rest mass, that each particle has rest mass 1. So this is the way the Vlasov equation looks like. And then the matter terms in terms of this function f then takes the following form when you're using those coordinates for the momentum L and W. And recall how E was the square root of 1 plus W squared plus L over R squared. And then you can see that 3 out of those 4 quantities are actually non-negative. The only quantity that has no sign is the current J, because W here can take both negative and positive values, whereas the other kernels are non-negative, and F is also always non-negative. So this is the system that we are interested in. And now I will show you that it's possible to specify explicit conditions on the initial data that guarantee the formation of black holes. And I would like to do that in 2 steps. So first I focus on how should this data look like in space, not in momentum, but just in space. And so what I have in this picture is a macroscopic density rho, like this. And then you take some ADM as M, and you call R naught is then 2M. So you have this here. And what you do then is you put the majority of the matter outside this capital R naught between R star and R1. So R star is the radius between R naught and R1, and R1 should satisfy a certain relation here. And this little R naught is a number you pick, but in particular you put some matter in the interior here. I will get back to this. So therefore I call this piece of matter the inner matter, and this piece of matter the outer part. And then remember now, this is the little R naught just to the right of the interior matter, and this is the capital R naught, which is to the left of the outer matter. So let me now specify conditions on the momenta for the initial density function f. So what you do is the following. So you pick a number, which I call here W minus, which is a negative number. And I have taken this form in terms of those parameters, and I call it gamma. And then you require that initially, in the support of your density function, all particles have radial momenta less or equal to this W minus. So this is a negative number, so this means that they're at least that negative. So that means that the particles are ingoing. And you also specify conditions on the angular momentum. It should satisfy this relation, where the M ring here is initial quasi-local mass or Hawking mass. And one can show that it is not an empty set of data, but you can really find such functions f having this property. And so those conditions are very important on the momenta. I call those the general support condition. So you should think of them that as your particles are ingoing quite fast, and also the angular momenta satisfy a certain relation. Should, before I proceed here, just say that if you think about the picture I had before, you saw that the matter was not so far outside this radius R0, which was equal to 2m. This means in practice that your this relation 2m over r will be less than 1, but it will not be far from 1. So in the setup I am discussing now, I'm actually having a situation where I'm not so far from having a trap surface. I should say that in those coordinates, I cannot really have a situation where 2m over r is equal to 1, but I can get arbitrarily close. But as I mentioned before, you would in principle like to be able to specify data where your quantity 2m over r initially is arbitrarily small and still guarantee the formation of a black hole. And this is actually possible, which I did in a work from 2012. And that is to combine what I now will describe with a result on global existence for rapidly outgoing matter. So since you can prove global existence, you have very good control of what's going on for rapidly outgoing matter. And therefore, the matter goes rapidly outwards, which means that this 2m over r will be very small far out. So then you can start your time there and reverse the time direction. So then you will come back to the situation we are in now, where particles are actually rapidly ingoing. Okay. And the setup here is as follows. You study the system on the domain D, where D is this region in space-time, where the gamma plus is the outgoing radial null geodesy originating from this R0. That was the little R0 just to the right of the interior matter. That is the gamma plus is a solution of this equation. Of course, you don't know this, you don't know mu and lambda a priori. It's a part of your solution, so there in the end there will be a bootstrap argument here. And we will also consider the ingoing null geodesic originating from capital R naught. So that is to the left of the outer matter. So you can think of those null geodesics, gamma plus and gamma minus, that they sort of act as barriers for the inner and outer matter respectively. And what we can prove is the following. So you specify those parameters as I have described, and you specify conditions on the initial data in momentum space as I have described. That is what I call the initial data set I. And then if you pick an initial datum in this set, then the solution has the following property, that this outgoing null geodesic will not reach infinity. It will terminate at a finite value, which I call gamma plus infinity. And the ingoing one, which starts further out, it will not cross this. It will also have a finite value, but larger than this gamma plus infinity. So that gamma plus and gamma minus, they will not intersect. And this is sort of, in this way, you have quite good control of what's going on, and it reflects this fact that the lapse function actually collapses, so that matter eventually will move very slowly close to the event horizon. And let me get back to that. But before, I can say that Theorem 1 leads to the following theorem, which I call Theorem 2. That is, there are positive constants alpha and beta, such that if you take positive time and an r coordinate outside 2m plus some small number here, if t is large, then f will be 0. That is, we have vacuum. And the metric equals the Schwarzschild metric representing a black hole of mass m. And moreover, if you can also really find the generator of the event horizon in the following way. So if you define r star as a supremum of all areal radius greater than r naught, such that the outgoing null geodesic has a finite limit, and then you define gamma star to be the radial outgoing null geodesic, which starts at this r star, then this will be sort of the generator of the event horizon. So in this way, we can sort of show that we have formed a black hole. And I have not said so much about this interior matter. Note that the interior matter, it is not in this domain D. So in principle, we don't care what it does, because it will never cross this outgoing null geodesic, which acts as a barrier. But one choice, which is particularly interesting, is if you choose this inner matter to be a static solution, then what we have shown is actually that our solution exists globally in time, despite the fact that a black hole forms. And this is, one should then know that Moncrief and Erdely already in 1981 conjectured that even if you form black holes, then it is likely that global existence hold in certain coordinates. That such coordinates are typically called singularity voiding. And Moncrief and Erdely typically had in mind maximum slicing or a constant mean curvature slicing and so on, but also similar properties for Schwarzschild in Schwarzschild coordinates. But this result, this corollary, to my knowledge, is the only result where one has really proven this rigorously, that the solution exists globally in time when you form a black hole. Okay, so I would like just to sketch a little bit of the proof for this result, because there is one ingredient in particular which I find particularly interesting here, and that is what I will call the ingoing lemma. And in order to see how this goes, I just introduce a few quantities here. So first of all, again, this quasi-local mass that is given by this here, and if you can actually express your quantity, one of the metric functions, in terms of this quantity m straightforwardly by solving the Einstein equations, and then you have this relation. And the lapse function mu, I split in two parts, mu hat and mu check, and they can be written like that. And why I do this is that I want to sort of have control of how the decay behavior of mu, and I will show you that one can get a decay of this mu hat. And the main mechanism for this is what I call the ingoing lemma. So one should have in mind that if you study Vlasov equation generally or kinetic matter, the particles can behave in sort of very complicated ways, right? You can specify initial data where particles go outward and inward and so on, and the dynamics will be very complicated. The ingoing lemma that I have on the slide here, it will make the situation much simplified, because those conditions I have given on the initial data, they will actually guarantee that the particles will continue to go inward for all time. And that, of course, simplifies the dynamics a lot. And so you simply take, let F not be regular and satisfy what I call the generous support condition, that was that the radial momenta was all negative with a certain value, and that the angular momentum satisfied a certain relation. Then one can show that for all radial momenta in the support of F for any time will be less or equal to this quantity. And remember that W minus was a negative number. So little w will be negative. And in particular, this gives you a sign on the current 4 times. And you do this by bootstraps. There will at least be some time interval where you know that particles are going inward, and that you follows by continuity. And on this time interval, you know the sign on your J, the current. And what you want now to do is to study, you take a characteristic, that is, you follow a particle, and you want to see how its radial momenta changes along this characteristic, along its path. And it is given by this equation. We have the metric coefficients here, derivative, time derivative of lambda, and the R derivative mu and so on. And you almost consider that equation, but you actually consider the combination of e to the minus lambda times w. And what then happens is the following, that you get a certain term here that drops out, which has this form in the bracket here, where now the w and e are those quantities along this characteristic, but the j and the rho and p, they are the components from the energy momentum tensor that you have got from integrating over all particles with different momentum. So if you write out the integrals for those quantities, it turns out that this term here can be written in this form. And the nice surprise then is that it is a square, so it has a sign. So a negative sign there, and this is positive. And of course, you want to show that this continues to be negative, so a negative contribution is good, and you can drop it. So then the terms that remain are the last 2 terms here, those ones. And then you simply use that on this time interval that you're considering, you know a sign on J. And that means from the Einstein equations that you actually know the behavior of this function m, which comes in here. And it's always increasing then, so you can replace m by its initial value. So you don't, this doesn't hurt. And therefore, you end up with the following bound or inequality, which you can write in this form. And therefore, you have now got something where you basically only have initial values coming in here. And this is exactly this condition for the what I call the generous support condition in terms of the angular momentum. So therefore, if you now make sure that this is negative, you can conclude knowing something about the lambda function, which you can derive, that in fact, along a characteristic, the radial momenta will stay strictly negative for all times. And then you can sort of make the bootstrap argument so that it holds for all the way to t equal to infinity. And this is, as I said, very useful because now you know the dynamics of your particles. And just quickly show you how you use this ingoing lemma to get some decay of the metric coefficient. So what you want to do is to show that those outgoing and ingoing null geodesics actually never intersect. So you want to, in some sense, show that this lapse function collapses. And so you start out with those curves, and you know that they at least satisfy this relation on some time interval. And you do this again with a bootstrap argument. And in this case, we know that the momenta are negative. I put the modulus sign here, so then they are greater than 0 instead. But at least the W, the radial momenta in your support, is always greater than 1. And the nice thing with this is that you can actually bound your energy density in terms of the current, because the kernel for the energy density can actually split so that you get 3 terms here. And each of those terms, thanks to this information from the ingoing lemma, can be estimated in terms of the modulus of J. So recall again that in a normal general situation, you have no idea what the sign of J is, but in this particular case, you actually can use J to get a bound of rho in this sense. And why this is important is that J determines the decay of mu. So I will be quick here, just say that the Einstein equations give you some relation of this type where you have rho plus p coming in, but since p is always less than rho, you can replace this by 2 rho. And you know from the previous slide that rho was less than 3j, 3 times the modulus of j, so you can replace this quantity by 6 times the modulus of j. And then some estimate, and then finally you see that you get, this is exactly the time derivative of your part of the metric function, which I call mu hat. So then you get an estimate of this type. And if you do the details, you can show that this part in bracket is actually strictly positive, which means that this thing is strictly negative. And this is sufficient to show sort of the collapse of the lapse. And that means that your ingoing and outgoing null geodesics will never intersect. And one can see this in a numerical simulation as follows. So in this picture here, I have the radius r here, and the blue curve here denotes the outer matter. And I should stress that in the numerical simulation, I don't need the inner matter. So I should immediately say that the inner matter that I have been talking about in this setup is due to technical reason. I need it in order to prove rigorously that you can do this. When you do numerical simulations, it seems not to be necessary to have this inner matter. So in this case, I do not have any inner matter. And then the red part here is simply that what has happened to the initial energy density at a later time. And you see that the particles simply move inwards. So this is what this describes. So the axis, y-axis, should not be time for those things. It is really the amplitude of the energy density. However, the time is relevant for those curves here because they denote null geodesics that I release at different times. So you see here, the blue curve is a null geodesic which is released at basically time 1.8 or something. And you see that it will go all the way to infinity. Likewise for the red one. whereas the green one will be captured. And that will basically be the event horizon. And you see also that, so the matter you see, which is consistent with the ingoing lemma, it moves inward all the time, but it slows up. And at this, close to this event horizon, it basically freezes, it continues to go inward, but very, very slowly. Which is basically what we prove analytically. So in this case, you can see quite nicely, I think, how a black hole is formed. So I think, I don't know, when I have talked by email with you, Martin, I got the impression that I should talk roughly 2 times 45 minutes, and there should be a little break in between. I can go on if you like, but if you want a break, you can take one. Please let me know.
I think it's a good time if anybody has any questions. We can take a couple of minutes. I guess I have a small question, which is related to something you said earlier. When you say far from trapped surfaces, so initial data that's far from having one, what is the characterization of far in this case?
So I would say that this quantity 2m/r is small. So if you have a trapped surface in those coordinates, it is, again, you cannot really have trapped surface in the particular coordinates I have chosen here, because Schwarzschild coordinates do not admit that, but roughly it means that 2m/r should be very close to 1. So when I say far from, I want a situation where 2m/r for my matter is small. And that I can achieve, as I mentioned, with combining what I have discussed now with a global existence result for rapidly outgoing matter.
Are there any other questions? All right, then in that case, yeah, I suggest that you keep going.
Okay. So therefore I have, if you go back to my slide where I had different questions about gravitational collapse, I have covered 3 of those questions, I think. So there are 4 remaining. That is for the second part here. And the main question that I will spend most time on is this issue about gravitational collapse for dust versus Vlasov. And again, why this is particularly interesting is that dust, you as we will see here, you can understand gravitational collapse in dust very well. You can basically get a semi-explicit solution, and you understand it quite well. But you also know that for dust, you can pose initial data which generically lead to naked singularities. That is, weak cosmic censorship is violated. Now, as we will see, Vlasov and dust are still quite related in the sense that you can approximate dust arbitrarily well with Vlasov matter. So then, of course, if you like cosmic censorship and you like Vlasov, you want to, your wish is that cosmic censorship should hold for Vlasov matter, but then it seems worrying that if you combine what I just said, that you can approximate dust arbitrarily well with Vlasov, but still dust, there are data for dust which leads to generic naked singularities. Then you're really interested in what will happen if you take such data for Vlasov, and you still want to be very close to dust. But before entering into this question, I will say more general things about dust and the relation to Vlasov, and also consider a case in Newtonian gravity, which gives some a priori insights, so to speak. Okay, so let me just say the following then. So the Vlasov equation is linear in F, and distributional solutions make sense. And one class of distributional solutions is given by the following ansatz for F, and it takes this form, and you see in particular that you have a Dirac delta distribution in the momentum space here. So here rho is a density, and UA is mapping from space-time into the mass shell, and U naught is given by UA from the mass shell relation. So this means that solutions of the Einstein-Vlasov system, where the phase space density F has this form, they are in one-to-one correspondence with dust solutions of the Einstein equations with density rho and 4 velocity U alpha. So you can consider dust as a singular case of matter described by the Vlasov equation. So I should say, for us who are working on the Einstein-Vlasov system, we do not consider distributional solution as Vlasov matter. We really think that to be dust. So when we talk about Vlasov matter, we always have a regular F in mind. But still, you can think of Vlasov matter as dust being a singular case described by the Vlasov equation. And if we first consider Newtonian gravity, then the corresponding systems are the pressureless Euler-Poisson system, which is on the dust side, and you have the Vlasov-Poisson system on the kinetic side. And you see that they solve the same Poisson equation and a little bit different transport equations. And now you ask what happens here. So it turns out that when you have the Euler-Poisson system, you can actually solve quite explicitly here in the following way. If you let your density have the following form, constant times 1 over r cubed, where r is a function depending on t, which solves this ordinary differential equation, where initially r is just 1 and r dot is just 0. So basically stands still. And then you have the characteristic equation here where B is the ball of radius r. And then you can define the velocity in this way. And if you do that, and if you determine capital U via the Poisson equation, then it turns out that the rho and the U and the capital U solves the Euler-Poisson system. And then you can analyze this ordinary differential equation and the second order ordinary differential equation, and you can conclude that there is a time, capital T, such that this function r goes to 0 when t goes to capital T. So this means that the solution describes a ball of dust initially at rest, which collapses under its own gravitational field to a point in finite time. And now you do the same game, but for the Vlasov equation instead. So we swap matter model. I should just move this bar here because it's okay. And use Vlasov instead for dust. And then, as I have mentioned before, this result by Pfaffenmoser and Leons per term, they have shown that independently of initial data, the solution exists globally in time, and there cannot be any blow up. So something else will happen here. Those global existence results, they say nothing about the behavior for such solutions, only that they will not break down. And in a work by Gerhard Rhein and a student of his, Taggart, they investigated this question a bit more carefully. And what they came up with is that for any positive constants, C1 and C2, there exists a smooth spherical symmetric solution F of the Vlasov-Poisson system, such that initially you can start with a density, which is very small, but at some time, the density can be arbitrarily large. So this means roughly what this result says is that, yes, you can mimic the behavior of dust, but you will never create infinite density. You will never have a blow up. but you can approximate the situation quite well. And the nicest thing to think about this, I think, is the following. So in the case of dust, if you think of the situation that you have a ring where you place your particles, and then they are initially at rest, and then you start the evolution, then they will move at exactly the same speed towards the center. That means that they will reach the center exactly at the same time. And this is what leads to this infinite density and the blow up. When you have Vlasov instead, even if you approximate dust very, very well, that means that you start with the particles, they are almost at rest. But since you have Vlasov, they are not allowed to be perfect at rest, because then you need this Dirac. I just have to admit some person. Then you, so they are not perfectly at rest, right? So they have small dispersions. So this means that when you evolve, the particles will also go to the center, but they will not reach the center exactly at the same time. So you can create very large densities, but not infinite density. So this, I think, is the mechanism which makes solutions in those two cases quite different. Of course, the situation in generativity is very different in the sense that you know, as we just saw a few minutes ago, that you can pose initial data such that singularities form, in the sense that a black hole is formed. So even for Vlasov. But this mechanism that I just described in Newtonian gravity is still important in some sense, because that, as we will see, a similar mechanism will play a role in the situation when we consider data which leads to naked singularity for dust, which likely will go away in the case of the Poisson system. So this reminds me that what I'm talking about now is a work in progress, in preparation with Gerhard Rhein. We have been doing this for quite some time, and hopefully we will be able to get some definite results out soon. But anyway, so this now I leave Newtonian gravity. This was just an example, and I get into dust collapse in generativity. And I've already mentioned the celebrated Oppenheimer-Schneider collapse from 1939, which has had an immense impact in generativity. And after that paper, there have been enormous amount of papers also in the case of an inhomogeneous collapse. And in particular, so this particular slide I show you now, I think I constructed a year ago or something, because I just went to archive and because I wanted to indicate that there is a community that really study the formation of naked singularities. So you see in the abstract here, we show that a directionally, globally naked singularity can be formed, and so on. So the issue is basically in this community, the naked singularities that form in dust are taken seriously, but what we want to show is that if you just perturb your matter model from dust to Vlasov, those naked singularities will go away. Again, this is a work in preparation. I don't know if this is the case, but I find it quite interesting in the sense that so much literature on the formation of naked singularities in the dust community. So let me quickly review dust collapse in generativity. And in this situation, you typically use co-moving coordinates. And you parameterize your metric in the following way. So you have your metric function lambda and this capital R, which is sort of the, depends now on time and little r. And you see that in this case, you have no lapse function, it's just one all the time. And you also have some boundary conditions to ensure asymptotic flatness and regular center. And then if you formulate your Einstein-dust system, you have the Euler equations coupled to the Einstein equations, and the way you formulate your energy momentum tensor is as in equation 6 here. But now, in co-moving coordinates, if you require that the forward velocity initially is given by just this simple expression here, so this is when upper index, and this is when you have the lower index, then it turns out that this actually solves equation 4, which was this part of the Euler equation, for all times, due to the fact that the Christoffel symbols, in this case for a metric of this form that I have specified, those components are always 0. So therefore, you have sort of got rid of the u. You already know how it looks like. And therefore, this also have an implication for how the energy momentum tensor looks like. And there is only one non-trivial component, and that is the energy density. All other components are 0. So that is, recall that dust is typically expressed as a pressureless fluid. You don't have any pressure. And this is what you see here. And the continuity equation 5 now becomes this simplified equation. So this is your system in some sense, but you should couple it now to the Einstein equations, which look like this. It's not so important for this talk. You just see some mess in the left-hand side, but more importantly, in the right-hand side, you see that the only component which is non-trivial now is the energy density. If you instead take the Einstein-Vlasov system, you will also have the current, the radial pressure, and the tangential pressure coming into the right-hand side. Then you prescribe some initial data here. So you take an initial data for your energy density rho, for your metric function capital R in this way, and for the time derivative of capital R. And then it turns out that thanks to the fact that most of the right-hand sides in the previous equations were 0, it means you can actually solve those equations quite nicely. So what you do is, if you now, given initial data, as I just mentioned, if you now define this quantity m of R in this way, so here are those quantities that you had from the initial data, and also this capital W, if you define it to be this quantity, which is now also just in terms of initial data, then if you now can solve what I call the master equation. So the master equation is this equation here, and you see that the only unknown is you have dt capital R, and you have also capital R in the right-hand side, but the other quantities on the right-hand side are just given in terms of initial data. So assume you can solve this master equation, then it turns out that then you can write down formulas for the metric function lambda. It is just this quantity here, and for the density, it is just this quantity here. So you have initial data in the numerator and the capital R, which depends on time, in the denominator. And it turns out that this master equation you can actually solve quite generally in terms of special functions. I will not go into exactly how you do that, but that is the fact. And that is one reason why dust collapse is so popular, because you can really get almost explicit solutions, at least semi-explicit solutions. And if you analyze a little bit more carefully the behavior of this capital R, you will find out that there is a function T0, which depends generally on little r, such that capital R will go to 0 as time goes to T0 of R. So T0 of R is the coordinate time by which the dust particle, which started out initially at R, has reached the center. So it means that the solution blows up at this T0 of R. So I call this the blow up time. Moreover, you can also introduce a function TH, which is a time when a trapped surface forms. And the general condition for trapped surface in the given coordinates is that along all radial null geodesics, this quantity should be less than 0. So you have that the area of the area radius, so to speak, that really decreases independently if you go outwards or inwards. And it turns out that this condition is actually equivalent to the well-known condition that you have like 2m over r is greater or equal to 1. But it's not so important for what I'm discussing now. The only thing that is important is that you can sort of obtain in particular situations formulas for T naught of r and TH of r. And that is, if I now go to sort of the initial case study by Oppenheim and Schneider, then you can compute those quantities very easily. So what they did in 1939 was to specify initial data, which in our case means that this W of R is just identically 1. And the initial value for the density function is just that it's a constant times. So it's between radius 0 and 1, it's just the amplitude of the density is just C, and then outside the radius 1 is just 0. And then you can actually solve those equations, this master equation, and you get an explicit solution in this case, which takes this form as follows. So you have first a factor which depends on time, which I have a shorthand which I call gamma of t here, which will be useful later, times r. And you see that the density, how it behaves. So initially this gamma is just 1. That is you see that initially the density was just amplitude c. But this gamma, as you see, will go to 0, which means that the rho will blow up at the blow up time t naught. And in this case, the blow up time t naught is independent of r. It's just a constant. It's 1 divided by square root of 6 pi c. And you get your metric function lambda just by taking the derivative with respect to little r of this capital R. And the formula for the trapped surface in this case is given by this function here. And in this situation, it turns out that weak cosmic censorship holds and things are nice. Before going further and discussing naked singularities and so on, let me just take a little break in the sense that one thing which is quite interesting generally about what I just showed you in this Oppenheimer-Schneider solution is that independently of the size of your amplitude C, the solution will blow up. It's just that the blow up will occur later if you take C to be small. So you can say that the Einstein-dust system is unstable. Because even if you take a very, very small perturbation, you will end up with having a singularity in a black hole. So then, how does this relate to the stability results for the Einstein-Vlasov system? Because as I've already indicated, if you take small initial data, then global existence has been shown for the Einstein-Vlasov system. And this was done first in the spherically symmetric case by Gerhard Rhine and Alan Rendell in 1992. And more recently, Lindblad and Taylor, and independently, Feynman and Chaudieu and Smulevici have proved this without the assumption of spherical symmetry. So if you take a small data in terms of f, so that means that f should be small, then you can show global existence. So this, you see, is quite different from what we have in dust. So what is the reason for this, and how is this related? And yes?
Is there a jump in the Vlasov case?
Pardon me, is there?
For the dust is completely supported, and the dust is sort of the density has a jump, right?
Well, so I mean, I think you mean that in the dust case you have this sharp boundary there.
Yeah.
Right. But this will not be important for this.
Okay.
When I will eventually approximate this dust situation, I will actually have a smooth boundary. So I will have a nice cutoff, so to speak. But for this particular issue that I am discussing now, I think the following is the mechanism instead, and that is, you should have in mind the following: that if you want to approximate dust, you should choose your function f roughly as a product of a Dirac delta function, but only approximate Dirac delta function, because if you take a Dirac delta function, then you are in the dust case. So this is approximate Dirac delta function in momentum space, which the momentum I have now called V here in this slide. And here is the macroscopic density rho. So basically, you have two parameters. You have one epsilon, and you have the C, which is the amplitude of the macroscopic density. And the point is now that if you, for instance, now fix the C, so you just decide, okay, C should be small, but it's fixed. And then you say, and now I want to approximate dust extremely well. This means that I need to take an epsilon, which is very, very small. But then you see, of course, that this sort of approximate Dirac delta function will, the amplitude of this will increase drastically, so that the product of H times rho naught, rho ring, even if rho ring has this C, will still be very large. So this means that the amplitude of F initially will not be small, and therefore those results that ensure that dispersion will occur are not valid. On the other hand, if you do the opposite, you first fix epsilon. So you say, I want to approximate dust, but I specify to which accuracy, so to speak. I take a small epsilon, but fix it. And then I say, okay, but now I want to choose a very small macroscopic density rho here. So that means that I take a very, very small C. Then, of course, your amplitude of F will also be small. And then you'll have dispersion in global existence. So it is nothing, there are no contradictions here. It's just things work as they should. But still, you see that there's a fundamental difference between dust and Vlasov matter, also concerning this result about dispersion, right? So you cannot have dispersion at all in the case of dust. Now I want to discuss Einstein-Vlasov system in the sense that I want to consider and approximate gravitational collapse of dust as well as I can. And in particular, I will consider the case with naked singularities. So now just let me just mention that, of course, in kinetic theory, the movement of the particles is complex, and one cannot speak about co-moving coordinates literally. However, in order to compare solutions for dust and for the EV system, it is convenient to use the same type of coordinates. And this is what I did with Gerhard Rhein when we started this project a number of years ago. It unfortunately turned out that local existence fails at the origin, co-moving coordinates. We have now used other coordinates where we can show local existence, and which are also nice for dust. So we are on the good side, so to speak. But I will anyway make the discussion in co-moving coordinates to be easy to compare with dust. And what I basically can do with Gerhard Rhein, as I said, this is a work in preparation, is that you can approximate, particularly the Oppenheimer-Schneider dust solutions, arbitrarily well by a solution of the Einstein-Vlasov system on any time interval 0 to capital T, where capital T is strictly less than the blow-up time. So if you simply give me a capital T which is less than this blow-up time, then I'm able to choose a sufficiently small epsilon such that I can mimic the behavior of dust by solutions to the Einstein-Vlasov system. And as you remarked here, it's exactly this remark that I have here, that in contrast to the dust solutions, the boundary at sort of initially, if you have this boundary at r equal to 1, this will not be just discontinuity. It will be a smooth boundary that is necessary when you study the Vlasov case. So we have roughly the following theorem which simply says what I've just described now, that you can approximate the Oppenheimer-Schneider-Dust solution arbitrarily well with a solution to the Einstein-Vlasov system. Now, we take the case that we are really interested in, and that is when you consider inhomogeneous initial data. So that, as we have seen, the Oppenheimer-Schneider solution, you had just a constant density that is a homogeneous case, but there are inhomogeneous data that lead to naked singularities for dust. And numerically, this was first studied by Early and Smar a long time ago, and then a rigorous proof was given by Christodoulou in 1984, and those are the papers where they have done this. And therefore, it's of course of great interest to evolve initial data for the Einstein-Vlasov system, having the property that analogous data for dust form naked singularities. And it's easier to go to the paper by Early and Smart to get really specific explicit data which lead to naked singularities. And they take the following form. So recall that in this homogeneous case, the rho was just a constant. Here it's a little bit more complicated. It depends on two parameters, theta and p here. And your function r, you take initially like this. And if you do that, then you can actually compute the blow-up time, which takes this form. And you can compute the time when a trap surface forms. And you see that if you pick now r equal to 0, then they will be the same. And what happens is, as a matter of fact, if you choose this theta and p in certain ways, then it turns out that null geodesics will escape to infinity from the singularity. And this one can see from the following picture. So in this case, I have taken now the critical value for theta in the case when I have chosen p to be 1 is roughly 6.3. So here I have chosen theta to be 6. And now you should be aware, here is the transition to vacuum. So that is why it looks a little bit strange at this point. But you see the red curve is just this T naught of r. When I have chosen p to be 1, it's just a straight line, right? And this black curve is the trap surface. And here I release null geodesics at later and later times, and the one that I release from the singularities were all at time 0. So this is the r equals 0 and time 0. I come from negative times here. And then the question is if such a null geodesic will cross the trap surface. If it does, then cosmic censorship holds. And in this case, you see that it does. However, if I increase the theta a little bit above 6.3, so I take 6.8 here, then also the null geodesic, which I release from the center here, will not cross the trap surface, and it will, in fact, then go to infinity. So, which means that you have a naked singularity. And now I want to just indicate what is the mechanism which is different from the Einstein-Vlasov system compared to dust, which might save cosmic censorship. I say might because I have not a rigorous proof at the moment, but I have good indications of what's going on. And the easiest way to see that this mechanism is actually to consider homogeneous solutions for the Einstein-Vlasov system. One can construct such solutions. Of course, you should then cut them off along some suitable curve to get exactly the situation for dust. But let us ignore that for a moment. Those homogeneous solutions, in that they have that the current must be 0, but both the radial pressure and the tangential pressure are both non-zero. And I find those solutions useful to understand the mechanisms which make dust and Vlasov behave very differently close to the blow up. And the point is the following. So if you remember how the energy density looked like in those coordinates W and L, they look similar also in those co-moving coordinates. So you have this quantity here. And you should then think about, if you start with a dust-like situation, then your support in momentum F, recall that the more dust-like you want it, the closer to a direct delta function you should take in momentum space. So this means that then those W's and L are restricted to be very, very small initially if you are close to dust. So this quantity here is basically just 1. However, if you consider, as you know, for Vlasov, you're not allowed to take a perfect Dirac function. It must be some dispersion. So those W's and L's, even if they initially are very small, they are not 0. And it turns out that since you now evolve and you have sort of a situation where you get close to this, what I call the blow-up time, things will start to behave quite drastic, in the sense that particles, which basically have almost 0 momentum initially, they will anyway get a lot of momentum eventually. So in some sense, of course, also the dust particles have kinetic energy because they move, but in co-moving coordinates, they don't move; they stand still, basically, right? They just whereas when W is not 0, you should think of it as a dispersion. It doesn't follow exactly the path of the dust particles. So what happens then for those homogeneous solutions that I have mentioned is the following: that the energy density for the Einstein-Vlasov system takes this form. So here I have this 1 over the gamma cube. Recall that gamma was this function which goes to 0 at the blow-up time. I have a tilde above it because it is not exactly the same function as in dust. It is very closely related. And then this integral here is in the case that epsilon is 0. That would be exactly the dust case. Then it would just be a number here, right? Not depending on this gamma function at all. So then you would have exactly that energy density for dust, and the energy density for Vlasov would be the same. And you recall that the energy density for dust was a constant divided by the cube of this scale factor gamma. But you see, there is a fundamental difference here, is that for Vlasov, epsilon is not 0. It is a small number, but not 0. So this means that when this quantity, gamma twiddle here, is getting close to 0, which it will, close to the blow-up time, this quantity will be very large. So the energy density for dust and for the Einstein-Vlasov system, they will eventually become very, very different. So in a sense, the contribution from the very small initial dispersion close to the blow-up time will make a major contribution and change the character of the energy density drastically. And this is what I think and hope will cure the naked singularities in dust, so that the cosmic censorship for such data holds for us. But it remains to be seen. But this is what I find important to really point out this mechanism. So if I just conclude what I've said about dust versus Vlasov, and what I hope that we can publish not too far in the future, is that you can approximate dust arbitrarily well with Vlasov matter, and that hopefully data which lead to naked singularities for dust will go away when you instead take such data for the Einstein-Vlasov system. Okay, so that was what I wanted to say about this Vlasov and dust in gravitational collapse. So then just a small remark on one more topic here, and that is, of course, you can ask more generally that can you form naked singularities at all? I mean, so what I just considered before was a particular set of data adapted to dust. But you can, of course, ask more generally, can you create data which lead to naked singularities? And of course, again, weak cosmic censorship can still hold if such data is not generic. And there are actually two works by Alan Rendell and Joan Velázquez from 2011 and 2017 when they tried to find such data. But they couldn't do it for the real model, but they took not the dust model, but something in between. That is, they took a Dirac delta in the radial momentum direction, but not in the tangential momentum direction. So it's some kind of dust-like model. And they also considered the massless case. In that particular case, they could find self-similar solutions. But so far, it's an open question if that can be generalized to the real Vlasov model. And I doubt, but who knows? So let me just summarize some open central questions in the spherical symmetric case. So again, the equations are not that complicated, but still sufficiently complicated that there are the most fundamental questions are still open. And those questions I have listed here, they are of course related, but you can basically ask yourself, can naked singularities form at all? Does the weak cosmic censorship conjecture hold? And this last question about weak cosmic censorship is tightly connected to the question of global existence for general initial data. Because if you cannot find data leading to naked singularities, then it's reasonable to believe that in fact solutions will exist globally in time. And if you can show that, then you will also be likely to show that weak cosmic censorship holds. But anyway, so those are some open questions that you can consider. So the last 10 minutes or so, I want to say something about critical collapse in spherical and in particular in axisymmetry. So critical collapse is a sort of a subtopic in gravitational collapse, and it was, I think, initially studied by Schwarzschild when he was studying the scalar field, inspired by the analytic works of Christodoulou. And what you do in critical collapse is that you fix an initial datum. I have called it phi here. And then you consider a family of initial data, which is A times phi. And A is called the amplitude. And then, depending on matter models, of course, but if you have in mind Vlasov matter or a scalar field, then it turns out, as I've been described here, that if you have a small initial data, that is, if you take a small amplitude, then you expect dispersion. Whereas if you take a large amplitude, you expect that a black hole will form. And then you can define a critical value as the lower limit of those values that lead to black hole formation. And then one distinguishes between type 1 and type 2 matter models. And examples of type 1, that is Vlasov matter, and also some Young-Mills matter models, those Young-Mills matter models which are associated with static solutions. And for type 2 matter models, then you have a scalar field, and that was, as I said, the original case studied by Schwarzschild, and also perfect fluid belongs to this category. And what does type 1 and type 2 mean? So one feature about type 1 and type 2 is the difference about the mass of a black hole you can form. So in this picture, I've just made a picture here to display what happens. So I have an amplitude on this axis, and I have assumed that the critical amplitude is 0.5, which is here, and here is the mass of the black hole I create. So for amplitudes lower than the critical value, there is no black hole, and therefore the mass is 0. And for type 2 matter, what happens is then that as soon as you get above the critical value, you start to create a black hole. But when you're very close to the critical value, this mass of the black hole for type 2 matter will be arbitrarily small and then increase. Whereas for type 1 matter, when you get to the critical value, you are not able to create black holes of arbitrarily small size. It will always take a substantial part of your initial mass of the data. So what I'm saying is that you start with some initial mass given by your initial data, and for type 1 matter, a substantial part of that mass will go into the black hole, roughly like 75 or 80% at least. And that is what is called the mass gap. And really it is a big difference between those types of matter. And what typically is associated with type 1 matter and type 2 matter is that if you ask yourself, what is the properties of the critical solution here? And then for type 1 matter, it turns out that the critical solution is typically an unstable stationary solution. And this is not universal. And that is not universal is easy to see in the following way. You can actually take any unstable stationary solution, for instance, for the Einstein-Vlasov system, and then you can use that as your initial datum, what I call phi on my previous slide. And then, of course, the critical amplitude would be A equal to 1 then. So, and you can choose any of those unstable stationary solutions. For type 2 matter, on the other hand, the critical solution is associated with the self-similar solution. And in that case, it turns out to be universal. There are other things that go into critical collapse concerning type 1 and type 2. There are different scaling laws and so on. I will not enter into this, but I just wanted to say something which is particular for Vlasov matter, that is type 1, and that you have really this mass gap, and that the solutions, when you are close to the critical value, really linger around the static or stationary solutions. You can see this in the evolutions. If you do numerical evolutions, when you get close to this critical value, the solution basically stands still for a while, and then it either disperses or form a black hole. Okay, and I should say, so in a more recent work by myself and Ellery Ames and Oliver Rinne, we studied critical collapse in the axisymmetric case, and in that case, the equations are far more complicated than in the spherical symmetric case, and there are no analytic results available. So we studied this by numerical means using a particle cell method, and I just, given the opportunity to give a talk here, I just have to have a slide where I have defined the binding energy, because that is a quantity which is extremely important when you are interested in to understand the asymptotics of your solutions, because it has a big impact about how the solution behaves. And the binding energy, or the what I call the fraction binding energy, because I have divided by m0 here, is the difference between the rest mass m0 and the ADM mass m. So typically you have either a positive sign of your binding energy or a negative sign. And this turns out to be a very important quantity for determining the asymptotic of your solutions. So for instance, when you study critical collapse, and if you take on the supercritical side, you collapse to a black hole, but then if you have your critical solution have a positive binding energy, then the solution undergoes a series of damped oscillations before collapsing to a black hole. Whereas in the case when this is negative, the solution basically collapses to a black hole straightforwardly. In this paper from 2021, there are links in this paper where you can watch some movies of those situations if you're interested. I should say that we can prove one thing in this paper analytically, and that is the case if, which I call complete dispersion. So if you have small amplitudes and then all matter will disperse. And then you can prove that then necessarily your binding energy will be less or equal to 0. Let me finish with something about axisymmetric collapse and the question of cosmic censorship. And I go back 30 years here. It was an article in the New York Times which says that computer defies Einstein's theory. A supercomputer at Cornell University simulating a tremendous gravitational collapse in the universe has startled and confounded astrophysicists by producing results that should not be possible according to Einstein's general theory of relativity. Well, so that what they refer to is actually cosmic censorship here. So it sounds as if Einstein had an idea about cosmic censorship, but it was too early for him. Anyway, the result that they refer to here is a result by Shapiro and Tucholsky, where they studied the Einstein-Vlasov system in axial symmetry, and they put matter along the axis in a sort of cigar-like distribution. So it was very elongated. And then they evolved and got indications that cosmic censorship is violated. This result was criticized by different people. Among those were Alan Rendell and Robert Wall and so on, but not until 2019, it was a serious simulation that redid this kind of simulation, and that was by William East. And I find that paper quite interesting because it shows very nicely, if you look at the evolution of such a cigar-like matter distribution, how matter is not sort of allowed to collapse when it is very elongated, because that sort of would violate the Hooke conjecture. So what happens is that matter ejects a lot of radiation, really a lot, and then finally redistributes itself so that the Hooke conjecture or the bounds for the Hooke conjecture are satisfied, and then it safely collapses to a black hole. So what East finds is that he gets support in favor of the weak cosmic censorship conjecture. Of course, there are no analytic results, so those are numerical results, but at least I would say that the support is now in favor for weak cosmic censorship. And then a similar thing, this is my last slide here, is that I have done a similar investigation with my colleagues Oliver and Hilary Ames, in the sense that we considered the case where you take a body where the modulus of the angular momentum is greater than the ADM mass squared. And the angular momentum in axisymmetry is a conserved quantity in the evolution. And then you can ask yourself, if you try to collapse such matter, you really force, you let the particles go inward with high speeds in order to try to collapse it. But in some sense, it should not be possible to collapse it, because if you collapse such matter and you create a black hole, then it's not really a black hole, because the curve solution which has the J greater than M squared will have a naked singularity. So cosmic censorship should sort of make sure that this cannot happen. So then we were curious to see what was going on here, and I have a little movie about this. Let me see if I can get to that point. Escape, no. Not able to get out of my, it's not really thank you yet, but here, okay, so here is like this, and then I am here. Okay, so I want to show you, it's not so easy to see exactly what's going on here, but if I mention what's going on, maybe you can understand. So let me pause here before I do something. And so basically what you see here is this direction is your z direction in axisymmetry. So this is the axis, and this is the axisymmetric radius, what I call rho typically. And you place matter here. So if it goes inwards in this direction, it gets close to the axis of symmetry. And again, this body now has a lot of angular momentum compared to the ADMS squared, so it should not be allowed to collapse. And what happens is, if you look carefully, is that you will see at the bottom of this matter configuration, it will make some oscillations, and in each oscillation, it will actually eject matter. So you can see some traces of this if you look carefully at the bottom. Of course, we have the data file, so we can see this more clearly. And what happens is that, so matter oscillates in and out in a certain number of oscillations and ejects matter towards which reach far out. And the remaining matter, the core of the matter, which sort of stays in the picture, it will eventually make the angular momentum lower. Of course, the total angular momentum for the full system is sort of preserved, but the core of the matter that eventually will collapse will have angular momentum which is less than the ADMS squared. So this, and as soon as this is achieved, as soon as the body has achieved to reverse this inequality, then it actually collapses to a black hole. So let's see if we can see this in this movie. So there you saw some traces of this ejection of matter if you look at the bottom there. And then it's finally collapses to a black hole. Oops. So let me get out of this and let me get into this again. Yeah, so, but I find this quite fascinating. I really like this in the sense that the equations are so aware of cosmic censorship in some sense. I find it quite amazing that as soon, if you measure the angular momentum of this body, which is sort of in the core of the picture, as soon as the inequality is reversed, that J is less than M squared, then it collapses. Oops.
The trick of working in any system,
I think this is, okay.
is to
My YouTube continually. Okay, so that was what I wanted to say today. So thank you for listening.
Thank you. Let's thank Håkan for a beautiful talk. That was really marvelous. Thank you, Håkan.
Thank you.
All right, so questions. Yep.
I have a question. First of all, thanks for the wonderful presentation. So do you believe that there are no naked singularities? So according to your sort of
if I believe there are no naked singularities for the Einstein-Vlasov system?
Yeah.
Yeah, it's it's a good question, because so a long time ago, it was actually Alan Rendell who conjectured that there are no naked singularities. And then I worked very hard on that problem for many years, and it almost killed me because I couldn't prove it, that there were no naked singularities. And then what happened was that Alan Rendell was sort of talked into a project by Velasquez. If you know Velasquez, if you look at his CV, many of his results is that you show blow up, and so on. And he sort of then persuaded Alan Rendell to try to show that you really get blow up and naked singularities for the Einstein-Vlasov system. And therefore they have those two papers that I mentioned, but they are not able to prove this. But they are on the way, so to speak. And what I do not like with their result, when I say do not like, because I want there to be no naked singularities, is that the case I really had problems with when I studied it by myself was a particular situation which I could not really treat. And their solution even if it's not for the real Vlasov system, but for a sort of dust-like model, it exactly is the case I couldn't do, so to speak. So I worry that this sort of borderline case, which I had problems with, is really a serious issue in some sense. So, which means that I can really not say anything in your question. I really don't know. I think it's a very interesting open question, and I personally hope there are no naked singularities, but I don't know. But I could say, I could cite Alan Rennell in the following way, that he had at least told me while he was in the business, he's not doing this anymore, but that if there are naked singularities, the measure sort of this set of initial data will be extremely small. If you compare it to the scalar field, of course, it has the measure is still 0, but it's not. If you compare it to the Vlasov, it would be 0 squared, so to speak, according to Alan Rennell. So it would be very, very special data.
Okay, thank you.
Any other questions?